Hi, in this video, I'm going to go through OCR AS-level Chemistry paper. This is paper 1, breadth in chemistry, and I'll just do the first half of this paper in this video and the second half in a later one. And this is the 2017 paper. So paper 1, 2017. Okay, so I've got the periodic table here. Which ion has a different number of electrons than the other three? So we're fairly familiar with all of these, probably except for gallium there. Okay, so let's have a look at the chloride ion. Well, there's chlorine there, so that's going to have 5. It's going to have like 5 electrons in the p shell. That's going to be 3s2, 3p5, because it's a single minus. It's got an extra one, so that's 3p6. Sulfur we can see is here, so that's going to be 3p4, 2 extra, so that's going to be 3p6. Calcium, well, that has got 4, it should have 4s2 in calcium there in the different color, but you've lost 2 of those electrons because there's a +2 ion, so that will also be 3s2 3p6. But we look at gallium. Now, gallium has got all of those electrons in the D shell as well, and then it's going to have, it will lost. So gallium electronic structure will be, I won't write all of it, but I'll write it's going to be 4s. It's going to be 4s2, 3d10, 4p. It's got 1 electron there, 4p1. So the 3+ ion then is going to be 3s. It's actually going to lose the electrons. It's going to lose 3 electrons. It will lose them from the first one from the 4p and the second from 4s. So the electronic structure of gallium will just be, will have 3. It will have 10 lots of 3d electrons. So gallium is different. Is the answer there. Okay, this is just working out the empirical formulae. So we need to work out a ratio of moles. So we've got reduced to the ratio of masses. If we have 100 grams of this compound, we're going to have 53.3 grams of carbon. Let's do that there. We'll have 11.1 grams of hydrogen, and we'll have 35.56 grams of oxygen. But we need to work out the ratio of moles, so we're going to use moles equal to mass over the atomic mass, AR. So that's going to be 53 over 12, 11.1 over 1, and 35.5 over 16. So if we work that out, we get 4.44 to 11.11 to 2.22. Divide by the smallest number to simplify the ratio. So we divide by 2.22. 4.4 over 2.22 is equal to 2. 11.11 over 2.22 is equal to 5. And that's obviously 1. So the formula is C2H5O. So D is the answer. Okay. Now, 4 samples of 4 hydrocarbons are completely burned under the same conditions of temperature and pressure, which will produce the greatest volume of CO2. Well, if we did a balanced equation, let's just do for the first one, C2H6, react it with oxygen. Now, we're going to get CO2 and H2O. Okay. Now, to balance that, obviously I need to put a 2 there. I need to put 3 there. Now, we don't really care about the water, but you can see that this is going to give us 2 moles of CO2 for every 1 mole of ethane. So the moles of CO2 there will be 0.4 multiplied by 2. Now, we wrote a balanced equation for that. You can see we'd get 3 moles of carbon dioxide for every 1 mole of that. So that's going to be 0.3 times 3. This one will give us 4 moles of carbon dioxide, so times 4. We've only got 0.2 to start off with, 0.2 times 4. This one will give us 5 moles. We start off with 0.1. So that gives us 0.8 moles of CO2. That gives us 0.9. think that's the highest one. That gives us 0.8 and that gives us 0.5. So our answer is B. Okay, which reaction produces the smallest atom economy of barium chloride? Now, if you're doing this multiple choice, you want to do it quickly, and so you don't work out the full atom economy, but don't forget that so we won't work out the full atom economy, but we can see here that the useful product, so atom economy is equal to useful over total mass of product. So in every case, we make 1 mole of barium chloride. So we just need to see which one is going to give us the most mass of all the other stuff, and that will give us the smallest atom economy. So look, 2 moles of water, 2 times 18, that's going to give us 36 grams of water for every 1 mole of barium chloride. That's going to give us 18 grams. This is the one with the highest amount of useless product. So 44 for the carbon dioxide plus 18. Well, you can see that's going to be a bigger, yeah. And this one is only going to give us 2 grams for hydrogen is very light. So this one gives us the biggest mass of useless products. So C has got the smallest atom economy. Okay. Okay, burette readings from a titration are shown below. The burette has an uncertainty in each reading. Okay, now you take 2 readings, initial reading and the final reading. So the total error is going to be plus or minus 0.1 centimeter cubed. Now what's the titer here? Well, the titer is 24.95 minus 5, which is equal to 19.95. So our percentage error then is going to be the uncertainty, which is 0.1, over the actual measurement, which is 19.95, multiplied by 100. That works out to be 0.5%. So D is the answer there. Okay, which atom has the greatest number of singly occupied orbitals? Okay, so let's have a look at carbon. So it's going to be full up here until carbon is going to be 2p, 2. And of course, remember the 2p orbitals, you get 1 electron in 1p and 1 in the next one. They don't pair up until they've got to. So carbon's got 2 unpaired electrons. Chlorine, well, that's 3p, 3p5. So that's going to have, that's just got this one, which is unpaired. That's got 1 unpaired electron. Calcium, right, calcium won't have any unpaired electrons because it's going to be, all of these orbitals are full up. And it's going to be 3p. So, sorry. Calcium is going to be, it's going to have a full p shell, 3p6, and then it's going to be 4s2. So those 2 electrons in the s orbital are going to be paired up, so that's got 0. Gallium, let's look at gallium here. Right, so gallium has got, everything's full up, it's got 4s2, and it's got 3d10, so they're all paired, and then it's 4p1. So gallium would have just 1 unpaired electron in the p orbital. So the answer is carbon, A. Which compound has polar molecules? Now looking at that, you've got an electronegative element, chlorine, attached to all of these 3. So much more electronegative than boron, carbon or sulfur. But they're not polar because they're all symmetrical. BCl3, that's only got 3 bonding pairs. So that's going to be trigonal planar, it's symmetrical. There's no lone pairs there. Carbon, of course, that's going to be 4 bonding pairs, so that's going to be tetrahedral, that's symmetrical. This has got 6 bonding pairs, so that's going to be octahedral, it's going to be symmetrical, no lone pairs. But if you look at OCl2, right, first of all, oxygen is more electronegative than chlorine, and oxygen always has 2 lone pairs and 2 bond pairs. So you can see that's not going to be symmetrical, that's going to be a bent shape. Chlorine is less electronegative than oxygen, so that will have a polar molecule, we'll have a dipole. So A is our answer there. Which element has the highest melting point? Well, phosphorus, sulfur and chlorine all exist as small molecules. If you remember, it's P4 molecules. Sulfur goes around as S8 molecules. Chlorine is Cl2 molecules. So all you're going to get there is you're going to get London forces between them, and pretty weak. So they're going to have low melting points. But silicon, you probably remember, is a giant covalent structure, very similar to diamond, each silicon forming 4 covalent bonds. Okay, so A is the answer there. What's the best explanation for the trend in boiling points down the halogen group? Well, as you remember, we've gone from F2 down to I2. Boiling points get higher. And the reason they get higher, well, what kind of, with small molecules, so what kind of intermolecular forces? Obviously, it's not going to be, none of these molecules are going to have a dipole, because both atoms in the molecule have the same electronegativity. So fluorine, yeah, very electronegative, but they're both very electronegative, so there's no dipole. So you're only going to get London forces in between them. So this is the answer here. Of course, this answer, when you boil a halogen, you do not break this bond here. You just separate the F2 molecule from another F2 molecule, so that's completely wrong. Hydrogen bonds, that's just rubbish, isn't it? Okay, this one is, they don't have permanent dipoles. Which silver compound is insoluble in concentrated ammonia? Insoluble. Right, now remember, when you're testing for halides, you add silver. Just do it for, and then if you've got a halide ion around, you add that, and you get AgBr, and that will give you a white precipitate, that will give you a cream precipitate, and that will give you a yellow precipitate. Now to distinguish them a little bit further, to make it a bit easier to tell which one you've got, you see if they'll dissolve in ammonia. The silver chloride will dissolve in aqueous ammonia. The AgBr will dissolve only in conc. Sorry, that's dilute aqueous ammonia, I should say. Whereas the AgI won't dissolve. It's not soluble even in conc ammonia. So this is going to be our answer here. And of course, silver nitrate is soluble whether or not it's in, but you've got ammonia added to the solution or not. Okay, now this is so this is about the temperature change you get when you neutralize 2 solutions. So we're going to think about 2 equations here. We're going to have Q is equal to mc delta T, and also that's the quantity of heat released during a reaction, and we're going to have delta H is equal to the quantity of heat released in the reaction divided by the number of moles N. Okay, so what I'm going to do is I'm going to substitute that value of delta H, that value of Q into there. So we're going to get delta H is equal to mc delta T over the number of moles N. Now we are interested in delta T, so I'm going to rearrange that to get delta T is equal to N multiplied by delta H divided by the mass of the solution and the specific heat capacity of water. Now you can see here that delta H is obviously, for the reaction, is constant. The specific heat capacity of water is constant, so the temperature is dependent on the number of moles. It's technically like temperature is proportional, temperature change is proportional to the number of moles over the mass of the solution. Right, so let's do the number of moles for this first reaction. Let's call it reaction 1. N is equal to conc times volume, 1 times So that's going to be 1 mole per decimeter cubed multiplied by 0.05 dm cubed is equal to 0.5. Let's do reaction 2. Oh, that's N. Let's do the mass of the solution for reaction 1. Well, we've got 50 centimeters cubed and 50, so that makes 100 grams. Let's do reaction 2. Well, the number of moles here is concentration times volume, so we've got 25 times 1 for both of the reagents, makes it easier. So concentration times volume, 1 times 0.025 is equal to 0.025. So we've got half the number of moles reacting. Okay, so that you might expect to make delta T half as big, but don't forget now, think about the mass of the water in reaction 2. Well, we've only got 25 centimeters cubed plus 25, so that's only 50, which is only half as big as this one here. So you can see, because reaction 1, you've got double the number of moles and double the mass, it's exactly the same. The delta T for both reactions is the same. So both experiments is the same. So it should be 6 degrees C. The answer is C. So just to say that in words, in the experiment 2, you've got only half the number of joules of energy being released, but you've only got half the mass of solution to warm up. So the overall temperature change is the same. Okay, this is just working out now. You've got to work out the enthalpy of combustion for, sorry, you haven't got to work out the enthalpy of combustion. You're given enthalpy of combustion data. Okay, you need to work out the enthalpy change for this reaction here. And coincidentally, that you can see that's probably equal to you can see that is actually the reaction for the enthalpy of formation of C4H10. You're forming it from its elements in the standard state. But we're given delta HC data. So when we draw a Hess's law cycle, what's the third thing we should write down at the bottom here? Well, we should write down the combustion products. And combustion products, of course, you burn all that lot, you're going to get CO2, 4 molecules of CO2 and 5 H2Os. Now we're burning these things, so which way should the arrows go? So we're going to put, they get turned into the combustion products. We've got to add oxygen, of course, and this will get turned into the, so the arrows go down. Let's write the numbers on there. Right, on this red arrow, we are burning 4 moles of carbon, so that's going to be 4 times 393.5. And it's going to be 5 times that for hydrogen, 5 times minus 285.8. We add all that up together, we get what is it? Minus 3003 kilojoules. Okay, so that's minus 3003. This one much more straightforward. All we've got to do is burn 1 mole of methane, so that's minus 2876.5. Now we need to work out this. This is the enthalpy. This is the enthalpy change we're going to find. So delta H is going to be equal to, right, we're following the red arrow, so that's going to be minus 303. And we're going against the green arrow, so we're going to change that sign to a plus 2876.5. Do that, you get an answer of minus 126.5 kilojoules. So our answer is that one, B. Okay. Right, the reversible reaction is below is allowed to reach equilibrium. What changes in condition we expect to shift the equilibrium towards the products to the right? Right, now let's think about pressure first of all. We have got 1 mole of hydrogen, 1 mole of iodine, and 2 moles of that. So we have got the same number of moles, same gaseous moles on both sides. So that means pressure will not affect the position of equilibrium. So straight away we can get rid of A and C. We need to just think about the temperature now. Look, this reaction is exothermic. So if we want to push it forwards, we need to raise the temperature. Le Chatelier tells us if you raise the temperature, lower the temperature, beg your pardon. Le Chatelier tells us if we lower the temperature, the reaction will move in the exo direction to try and warm up. So we're going to increase the temperature. So D is the right answer there. I didn't mean to do that. D is the right answer. My whiteboard gone slightly crazy there. Sorry about that. Okay, right. What is the systematic name of the compound below? Right, now you show stereoisomerism, so we've got all those E's and Z's there, but let's think about the name first of all. Where's our longest carbon chain? Well, it's 1, 2, 3, 4. Okay, so it's going to be bute, and it's got butene, so it's going to be but2ene, and we've got a bromine stuck on the number 2, so it's 2-bromo but2ene. Now we need to think, is it the E or the Z isomer? Okay, so right, let's think about the two carbons attached to the green one there. It's got a methyl group here, so that's which is 15 mass, and then we've got a bromine, so that's much heavier, so that's the highest priority group there. Let's think now about this other carbon. What's that got? It's got a methyl group here, and it's got a hydrogen there. I just draw the hydrogen on there. Obviously the methyl is the highest priority, so the two high priority groups are on the opposite side, so that's the E form, so it's E 2-bromobute2ene. Okay, 15. The skeletal formula of an organic compound is shown below. What is the molecular formula of this organic compound? Right, so I'm going to do how many carbon atoms? We've got 1, 2, 3, 4, 5, and another one here, 6, so it's C6. Now, it's convenient here. Whenever you've only got carbons, hydrogens, and oxygens, you can work out the number of hydrogens by just looking at the, if there's no double bonds, it's obviously going to be CnH2n plus 2. If you have any double bonds, either carbon-carbon or carbon-oxygen, like we've got there, you take away 2 hydrogens. So we've got one double bond there, so it's going to be C6H12, and we've got 2 oxygens, so that's O2. That's the answer there, which is this one. And if you want to just check that, so remember, any double bond, carbon-carbon or carbon-hydrogen, sorry, or carbon-oxygen, sorry, you lose 2 hydrogens. That only works if you've got carbon, hydrogen, and oxygen in there. If you've got nitrogen, that doesn't work. But a lot of the molecules we deal with do only have those 3 in it. It's quite a quick way of doing it. Let's just think we've got 3 on the methyl group there. You've got none on that carbon. You have got 1 hydrogen on there and another one there. You've got 1 hydrogen stuck to that, and you've got 3 there and 3 there. Add them up, that comes to 12. Okay, so it's all okay. Right. Now, how many structural isomers, so not stereo, have the formula C5H12? Right, so that's saturated, right? So you don't have to worry about double bonds. Tell it's saturated because it's Cn plus C2n plus 2 hydrogens, yeah. Right, how many isomers we've got? Right, we can have 5 in a straight line. That'd be pentane. Won't put the hydrogens on, that's 1. Then you could have 4 like that with a branch coming off. Now that branch can only be, if it goes on that carbon there, it's the same. So there's only one possible version of that. Or you could have 3 with 2 branches with 2, so you could have, the only place you can have branches are there and there. So the answer, there's just 3 isomers there. Okay, which compound has the lowest boiling point? So we need to just have a look at these first and see which is the biggest molecule. They're all hydrocarbons. So we're talking about, there's no dipole, so we're just talking about London forces. And of course, the bigger the molecule, the stronger the London forces, first of all. But you can see that they're all the same, okay? They're all saturated. So octane is going to be C8H18. Now you've got 8 carbons in this one because you've got a methyl heptis 7, 1 plus that 8 carbons there. This one is hex, so that's 6, but you've got 2 methyl groups, 2 plus 6, that's 8 carbons there. And this is 5 carbons, but you've got 3 methyls, so 3 plus 5, that makes 8. So they're all the same. So now we have to think about the shape of the molecule. Well, with London forces, the electrons need to be able to interact with each other. Effectively, the molecule has to have a large surface area, and the one which will have the biggest surface area will be the one which is a straight chain, which is octane. So that's going to have the highest boiling point. We're not asking for that though. The one with the maximum amount of branching, that's going to have the lowest. Well, you can see the maximum amounts of branching is going to be A. That one, that's going to be 1, 2, 3, 4, 5, and you're going to have branches 2, 3, and 4. That's going to be like that. Dimethyl hexane, 1, 2, 3, 4. Right, that's going to have a methyl there and there. And octane, obviously, methyl heptane is going to be, it's got one there, and octane is the straight chain. So this is the answer. Right, this is about infrared spectroscopy, and it is about alcohols. So alcohol A is heated under reflux with sulfuric acid and potassium dichromate. What does that do? That will oxidize alcohols, okay? It will oxidize a primary. Now, if it's under reflux, it's going to oxidize it all the way to a carboxylic acid. It'll go to an aldehyde, then to a carboxylic acid. The secondary, that will just go to a ketone. And a tertiary, of course, can't be oxidized. No oxidation. Right. So we need to think, which is this let's think, is it a tertiary alcohol, first of all? Now, if it's a tertiary alcohol, when you oxidize it, nothing happens. So you still have the OH group there. So the OH group for the alcohol is there. So you should have a big broad peak, a broadish peak between there, which is usually about there. And you always, with alcohols, you always get that. And this one next to it, by the way, I've drawn in red, that's due to the carbon-hydrogen bonds. Now, you haven't got that green peak, so we can say that this is not a tertiary alcohol. All right, definitely not. Now, we can also say it is not a primary alcohol because you will get a carboxylic acid there, and that gives you a very broad peak, quite close. And if I just draw it in the area there, I'll just rub that out. If it was a carboxylic acid, you would have, you get a really broad peak there for the carboxylic, okay, which looks like that. And it swallows up that one I did in red, it swallows up that CH there. So it's not carboxylic acid. So it really must be a secondary. Now let's just check that. If you've got a secondary alcohol, you should end up with a carbonyl group in there from the ketone. Have you got a carbonyl there? And you can see you've got it there. That's very characteristic of a carbonyl. There you go, there. There it is, and that's in the right place. So we've established this must be a secondary alcohol. So now let's look at our list of alcohols. Oh God, and that again. Let's look at our list of alcohols here. Right, we're looking for a secondary alcohol. Okay, so hopefully you'll be able to see that this is a tertiary alcohol because that carbon is attached to 3 others. 1, 2, 3, that's a tertiary. This one is a secondary alcohol because that carbon with the OH in it is attached to 2 carbons. That's a secondary. This one is a primary alcohol because the carbon it is attached to is only attached to one other one. It's a primary. And this is also a primary because that carbon is attached to just one other. So it's got to be B, the answer there. Okay, which alcohol is not likely to have a fragment of MZ43 in its spectrum? Right, now, if you know that a methyl group has, so an methyl group that's 15, an ethyl is, well, you've got another CH2, so that's going to be 29. A propyl group, you can see there, is going to be 43. Okay, so you can see most of those compounds would fragment with this propyl group is going to give you 43. So I'll just rub that out and then we'll have a look at that a bit more closely. Right, let's look at B. Well, you can see you've got a propyl group there. I won't draw these out because it's fairly obvious. If it's split where I draw my blue line there, you would end up getting the red propyl group. If this one's split, draw the blue line there, then you get a propyl group there. Now this one here, it's not quite a propyl group, but if it splits there, I'll do that in blue, it will give you that fragment there, and you think you can see that's also 43 because look, it's CH3, CH3. Okay, so you've got 15 there, 15 there makes 30, 12 there makes 42, and 1 makes 43, so that one could. So it's got to be A. Let's just have a look at A, and you think we'll draw a little structure of A. You can see that, let's draw it out a bit better. So you can see more easily. So you've got 1, 2, 3, 4 carbons in a row, and you've got an OH on that one, and there. Now, there's definitely no propyl group in there, as you can see. But you can also probably see there's no other way of getting 43, a fragment of 43. You might think, oh, what if we do this? This might look in the right sort of region, but I think that works out to be 42, that fragment there, okay? And there's no way you can get a 43 in that molecule. That one is the right answer, A. 21, off the multiple choice now. This is just the first section B question. Okay. Question is about 2-chloropropene, okay, which they've drawn here. Complete the flowchart to show the organic products. Okay, so there's our, we start off there. Hydrogen and nickel catalyst, what happens? You'll break that double bond there, and you'll stick a hydrogen to each carbon. So the product is going to look like, well, it's going to like this. I've got the new hydrogen there and a methyl group there. Now, if you react it with bromine, a very similar reaction, you don't need a catalyst for bromine, of course, is you break the double bond, then you end up with the bromine stuck to each of those carbons. So that's going to be, right, we've got a bromine there this time, and a bromine on the right-hand side carbon as well. That's our product. Right, and then I've had to copy it down twice because it's a bit too big otherwise. So what happens now, you react 2-chloropropene with steam, you get another addition reaction, just like with the H2. And so what you end up doing is you stick an H and an OH to the, and you break the double bond. But of course you can see there, that OH, it could either go to the blue carbon or to the green carbon. Now, we have to think about the intermediate here. Right, let's say if it sticks to the, let's say the first step in the reaction, the hydrogen sticks on first. Okay, so let's say the hydrogen sticks onto the blue carbon. Right, so the hydrogen is sticking on there. and we're going to have, that will be a carbocation. Now what kind of a carbocation is that? Is a secondary, sorry, it's a primary carbocation. Let's see what happens if it sticks onto the green one. When we're going to get something different, then we're going to get so it sticks onto the green one here, and we're going to have a positive charge on that one. Now you can see what kind of a carbocation is that? That's a secondary carbocation. Which is the most stable? It's the secondary, so that's one that's going to form to give you the major product, so we're not going to get that. Now that's then going to react with the other bit of the water molecule, the OH, so the OH is going to go on there. So that is going to be our major product, that one there. So that last bit is a bit more difficult than the other ones, okay? And it's a major product because it goes through the secondary carbocation. This one that goes through the primary would end up giving us the primary alcohol there, which you wouldn't get as much of that. That'd be the minor product. The reaction of 2-chloropropene with steam requires a catalyst. Okay, now you may remember the suitable catalyst is phosphoric acid, and you probably remember that in the context of when you react ethene with steam. And it's a pretty important industrial process to give you ethanol. And there you want steam and a phosphoric acid catalyst. That's probably where you've come across that. Right. 2-chloropropene can be polymerized. Okay, write a balanced equation for the formation of this polymer. Okay, so where have we got our? We've got our monomer there, 2-chloropropene. Okay, so right, so I'll draw that. It says it's got to be a balanced equation. So here we've got chlorine, methyl, hydrogen, and hydrogen. Right, when it polymerizes, they join up, so you're going to end up, they go next to each other to give that. And that's the repeating unit. Okay, so we should put a bracket around that. Now it does say a balanced equation, so we're going to say if you have n molecules of that, you're going to end up with a polymer which is going to be that many repeating units long, n repeating units long. So that's what they want you to write there. Okay. After their useful life, waste polymers can be disposed of by combustion. Right, one particular problem with burning this particular, okay, if you're burning hydrocarbons, it's not too bad, because a hydrocarbon, all you're going to get as the combustion product are CO2 and water if the temperature is high enough, so that's not too bad. Okay, but if you burn this, because you've got chlorine in there, you're also going to get some HCl, which is acidic, and that can't be released into the environment without being captured or something first. Okay, right, so that is as far as I'm going to go with that paper. I'll do the second half in the next video.